In this lesson, we're going to be learning about the conjugate root theorem and Descartes' rule of signs. For a warm-up, let's work these three problems and then pause the video, come back and check your solutions. Did you remember that I squared is equal to -1? So we've got a -24 times -1, positive 24. Again, negative I squared is going to make that -1, which is a positive 1. And remember, when we've got opposite signs in our binomials, it's going to eliminate the middle term. The conjugate root theorem. If p of x is a polynomial with rational coefficients, then the irrational roots of p of x occurs in pairs. So in other words, if one of your solutions is a minus the square root of b, then it's also going to have a solution of a plus the square root of b. The imaginary root theorem is similar. If you end up with a plus bi, then you're also going to have a minus bi as a root. So the conjugates will also be a root of your polynomial. Example 1, we have a cubic polynomial, p of x. We're told it has real coefficients, and one of the solutions is 2 minus 3i, and the other one is 3/4. And what is an additional root? Well, the conjugate root tells us if we've got 2 minus 3i, then we've also got 2 plus 3i. A quartic polynomial, p of x, so quartic, think how many exponents, x to the fourth, right, has real coefficients. If the square root of 3 and 6 minus 2i are two roots, what are the other two? Well, we know it's going to be 6 plus 2i and the negative square root of 3. That gives us 4 different roots. Now we're asked to find a third-degree polynomial with rational coefficients that has roots -2 and 2 minus I. So what we're going to have to do is actually, we're given the roots and we're going to have to work our way backwards in order to determine what the original polynomial is. We've done this before. We've got x plus 2, x minus 2 minus I, and x minus 2 plus I, because we've got third degree, so we need 3 different roots. We've got minus I, so our conjugate tells us we have to have 2 plus I. Now we're going to multiply these complex conjugates to get x squared minus 4x plus 5. Then we also need to multiply this binomial by the trinomial, and we get our third degree polynomial, x cubed minus 2x squared minus 3x plus 10. Pretty simple, huh? So let's learn about Descartes' rule of signs. First of all, we're going to let p of x be a polynomial with real coefficients that are written in standard form. Standard form, it's going in descending order by variable set equal to x. The number of positive real roots is either equal to the number of sign changes between consecutive coefficients or is less than by an even number. So think positive goes down by even numbers. So if you've got x to the fourth, then your possible solutions are going to be 4, 2, or 0. No odds in there. The number of negative real roots is either equal to the number of sign changes or less than by an even number. Here's our Descartes chart showing that we've got apparently x to the sixth. Today we're just looking at the positive and negative real zeros. We can either have 4, 2, or none, or 4 or 0. Notice they're even. What does Descartes' rule of signs tell you about the real roots of x to the third minus x squared plus 1? Notice that it's to the third power. So we could have 3 real roots. Let's write the coefficients of each of these terms. We've got 1, -1, and 1. So we've got a sign change here and another sign change here. So there are 2 different sign changes. So they're either 2 or 0 positive real roots. Now to find what negative real roots there would be, we simply find p of negative x. Your parentheses are so important here to hold your negative numbers. Negative x to the third is still negative x, but when we square it, it would be positive, but it's minus, so that turns it back to a negative root or a negative coefficient. No sign change here, but there's 1 here. So there's 1 sign change, so there is 1 negative real root. Excellent. You're ready to begin practice.